So today we are going to start the new chapter, that is the properties of pure substances. Okay, so first, what is the definition of pure substance? Homogeneous and invariable chemical composition irrespective of the phase. Okay, so he didn't explain about this definition, but what is our aim in this chapter actually? Why we are going to study this chapter? Okay, why we are going to study the properties of pure substance? All right, so generally we started our thermodynamics with the by learning the behavior of ideal gases, right? Behavior of ideal gases. So there were direct formulas. So, dh equal to cp du equal to cv dt. These formulas were there, okay, where internal energy was function of temperature and all. This is valid for only ideal gases, and for the ideal gases we can find the properties like from equations pv equal to mrt and all. Okay, so these were the things for the ideal gases, but generally here we are concerned about the real gases, and why we are going to learn what we are going to learn in this chapter. Generally in the vapor compression cycles, in the vapor cycles, generally we must know the various properties of the vapors, okay, various properties of the stream at different conditions, okay, different conditions. Okay, generally you can't use the equations of ideal gas equations. Okay, there are no direct formulas to find out the vapors. Okay, generally experimentally what they have done, they conducted experiments, and experimentally they found out the results of properties of substances, and they put in the form of the table, and we are going to utilize the table that is known as steam table. Okay, from the steam table we are going to get pressure. They will give pressure, temperature. At that pressure, temperature, what is the enthalpy, entropy, we are going to find out. Okay, that table, actually that table, where does the data came in the table? They conducted experiments. Through the experiments the data came. Okay, so there is a refrigerant table, that is there is a steam table, but there is no air table, because air is an ideal gas. We are going to find the properties of an ideal gas by using the equations. Okay, there are equations, certain set of equations, but here we are not going to uh, get the equations. Okay, just we have to find out from the different diagrams and stream tables. Okay, different properties of vapors and streams. Okay, so in this chapter we are going to discuss about the water. We are not going to discuss about the different substances again. Uh, right, so in this we are going to discuss only about the water. Okay, property of water, because once we know the pattern, how to find the different properties for water, for different fluids, the finding the properties that has the same pattern. Okay, see, we find out the properties for the water, right? So for the different fluids, similarly we can find the properties for the different fluids like we have find for the water. Okay, all right, so it has the same pattern. That's why it is the significant thing. Okay, so same way you can find the properties of different substances. Okay, so the fourth point is, this is important for Rankine cycle. Okay, Rankine cycle, where there is a phase change, where there is a steam. Okay, in the boilers, turbines, there is a steam, right? So we cannot use the formulas. Okay, generally previously it was air, dq equal to du plus dw. It was helium in the inside the piston cylinder assembly. Okay, inside the piston there was an ideal gas, so you use the ideal gas equation u2 minus u1. It is given as mcvdt. Okay, but here you can't use those equations first of all. Okay, in this thing you can't use those equations, because inside the piston cylinder you will give the phase change, or inside the piston cylinder you give the water or steam. But for the water or steam you cannot use the ideal gas equations. Okay, instead you can find out by using the uh, different stream tables, or we are going to discuss about those things. Okay, so again, the heat is classified into two types, right? A sensible heat and latent heat. Okay, sensible heat we discussed. What is latent heat actually? So the heat is divided into two types, sensible heat and latent heat. Okay, the heat associated with temperature is known as sensible heat, and the heat which is associated with the phase change is known as latent heat. Okay, generally in the heat transfer discussed about the there is actually temperature. What is energy? Energy, there is no definition for the energy. Energy means something must change. Okay, something must change. So what is temperature? Temperature is the wait representation of energy level inside. Okay, if nothing is changing, that means there is no energy. Okay, so As a thermal engineer, we are generally uh, our focus is based on temperatures and phase changes. Okay, chemical, electrical changes, mechanical changes. We are not concerned about. Okay, so temperature is a representation of energy level inside. Okay, degree of molecular activity is the soul of temperature. If the molecular activity is inside is very more, then temperature is very more. Molecular activity is less, than temperature is very less. Okay, so they will collide due to collision. Okay, they will collide due to uh, generally generally what is heat actually? Heat is temperature difference due to hmm, consequences of collision is a heat. Okay, heat is a consequence of collision actually. Okay, so generally when we look inside the body, there are millions and trillions of molecules. When you take the two molecules, suppose for example there will be intermolecular forces in between the two molecules. Okay, inside there will be a movement of the molecule. Okay, molecule will translate, rotate and vibrate at their own place. Okay, these are the molecular activities of molecule. If you want to change these activities, then temperature must increase or decrease. Okay, temperature must increase or decrease. Okay, it has it, to change these activities, we must supply some energy. They require some amount of energy. That energy is known as sensible heat. Okay, sensible heat. Generally when we supply the heat, then they supply the heat, then there will be, due to heat transfer, the molecules get energized. Okay, there will be molecular activity will increase. Molecular activity increases means temperature will increase. Okay, so for to increase the temperature from 0 to 100 degrees centigrade, the energy which is required, we can calculate by using equal to C is Q equal to mc dt. For the liquid, C is constant. Okay, for the solids and liquid, C is constant. For the gases, C is not constant. Okay, there will be change. So there is a little amount of change, right? So that's why we are treating it as constant. Okay, so 1 kg 4.1800, so we'll get 418 kilojoule per kg. This much amount of energy is required to increase the temperature from 0 to 100 degrees centigrade. So if I supply this amount of energy, suppose if I burn 100 or 112 matchstick or 110 matchstick, then the temperature of water, 1 kg of water will increase to, if the density of water is taken as 100,000, then uh, that is 1 liter of water. 1 liter of water to increase the temperature, I need 418 kilojoule per kg. Okay, this much amount of heat is required. So what does this heat will do? This energy will go to inside the molecules, and the molecular activity of the molecules will change. Okay, molecules will translate, rotate, vibrate. Okay, due to vibration there is a heat transfer, right? So the energy associated with the temperature, energy associated with the molecular activities known as sensible heat. All right, sensible heat. So energy associated with the phase change, generally there will be intermolecular forces in between the two molecules. Okay, in order to break these molecules, we need actually latent, in the sense hidden. It is a Greek word. Latent means hidden. Okay, so there will be huge intermolecular forces. To break these forces, I need to supply much more amount of heat. So I need to supply more amount of heat than the sensible heat. Okay, so to break the bonds in between the two molecules, so this is known as latent heat. Okay, so sir, how can you say that more energy is required? So just look at the equation. Okay, Q equal to ml. That what is the formula for the sensible? Q equal to ml, mass into latent heat. So from to convert 100 kg of steam to 100 kg of water to 100 degrees centigrade of water to the 1000 degrees and 100 degrees centigrade of steam, then how much heat I must supply for 1 liter? I must supply 2256. So 2256 I must supply. So look at this. Okay, so in order to make the ice, so ice. What is ice actually? Ice is near to the absolute temperature. Okay, ice has the energy actually. Ice has the energy. Okay, but when we at absolute zero, if you take a reference absolute zero, everything in the universe has the energy. Okay, ice also has the energy. Ice is minus 27 degrees centigrade, but minus 20 minus at 0 Kelvin, at 0 Kelvin uh, at 0 Kelvin, the entropy will be 0 and change in internal energy will be 0 at 0 Kelvin. Okay, so the at 0 Kelvin the energy will not be there. Okay, so ice has energy. Okay, so in order to change the ice into water, I must supply less amount of it when compared to sensible heat to change 0 to 100. Okay. So latent heat 335 kilojoule per kg Kelvin kilojoule per kg I need to supply to change the ice from 0 degrees to 0 degrees centigrade ice to 0 degrees centigrade water. Okay, this was the concept of latent heat and sensible heat. All right. थर्मोडाइनमिक्स में है ना ईच एंड एवरीथिंग चीज़ मिलती है अपने को कि थर्मोडाइनमिक्स अकॉर्डिंग टू थर्मोडाइनमिक्स कि टू ब्रेक द forces intermolecular forces means there is a bonding, right? So to break the forces we need to supply large amount of heat. Alright, we need to supply large amount of heat. Force again to to change the temperature we need less amount of heat. That is ये क्या बोलता बोला जनरली इन ए रिलेशनशिप तब कोई भी भड़का दिया तो इंसान को है ना चीज़ें आते रहती दिमाग में शायद ऐसा भी हो सकता बट योर बॉन्ड मस्ट बी दैट मच स्ट्रांग दैट बॉन्ड नहीं टूटना ठीक है बॉन्ड मस्ट नॉट ब्रेक ओके the bonding must be like that in the relationship. So if bond is weak then it requires less amount of energy, right, to break that bond in between the friends or you can take any type of relation friendships. So between the two friends if the bonding is weak then third person will come and he will he will tell you that he was telling so and so to you but if the bonding is strong then it is good. So to make the bonding strong you must be positivity must be there in between the two friends. Okay, so thermodynamics teaches you each and everything. So generally we are going to discuss about the phase transformation of pure substances. Okay, about the TS diagram. Suppose for example if there is a piston cylinder assembly, okay, some weight is placed. Okay, so generally inside there is a water. So what is the temperature of the water inside? It is P atmospheric temperature. And what is the temperature outside? Suppose the piston pressure is neglected. Okay, so temperature outside will be same as pressure inside. Okay, now we are at constant pressure we are heating, we are introducing some heat. So if we introduce some heat there will be sensible heat changes, right? So generally temperature will increase. If the temperature will increase in the heat addition process, constant pressure heat addition process, and what about entropy? Entropy will increase. Okay, once the temperature reaches to 100 degrees centigrade, then when I supply the heat, then there will be a phase change at constant temperature. So there will be a latent heat. Okay, latent heat line. Okay, so again after 100 degrees centigrade vapor, then again the temperature will increase and entropy will increase. Now what I am doing, I am going to increase the temperature, increase the pressure. Okay, once I increase the pressure, what happens to boiling point? Once I introduce the heat, okay, at constant pressure, suppose for example previously pressure was 100 atmospheric pressure, okay, 1 atmospheric, now 1.5 or 2 atmospheric. What happens to the boiling point temperature? Will increase or decrease? So to understand this, let's take one example of pressure cooker. Okay, so generally when we cook the food in the pressure cooker, generally the atmosphere will be P atmospheric atmospheric pressure and temperature will be room temperature. Okay, and once we introduce the heat when by closing the lid of the pressure cooker, then there will be a constant volume heat addition process. Okay, constant volume heat addition process, then pressure is going to increase and temperature is going to increase, but at one point pressure reaches its maximum capacity. Okay, maximum capacity in the first vessel. Okay, then there will be a constant pressure cooling process. Okay, constant pressure heating process. So at high pressure, what about the boiling point? Boiling point will increase. Okay, the temperature will increase. So you are confused, right? So boiling temperature will increase, so it must take the less time to get that temperature. You are thinking like this, right? So actually it is not like that. Okay, so generally for 130 to reach 130 degrees centigrade time it takes time, but at 130 degree temperature at that temperature the preparation of food will be easier. Okay, the food is prepared at that temperature, then it will take less time to prepare the food. at higher temperatures, right, when compared to lower temperatures. So that is the concept of faster cooking in the pressure cooker. Okay, so boiling point temperature will increase. So if you go through the hilly side areas, the pressure will be less, so boiling point temperature will be, suppose for example 50 degrees centigrade temperature is their boiling point. So it is difficult to cook the food because you can go up to in less pressure you can go up to 50-degree boiling point. You can boil the water at low temperatures. But in order to cook the food at low temperatures, it takes much more time, right. In the Himalayas when you go, so you can't cook the food fast. Okay, it will take time. Boiling point temperature, cooking the food does not depend upon the boiling point temperature. Boiling point temperature tells you that at what temperature water boils. Okay, preparation food is concerned with the higher temperature or lower temperature. If I cook at higher temperature, then it will be cooked in faster. If I cook at lower temperature, then it will be cooked uh, at slow rate. Okay, that is a concept. Okay, so in the hilly areas, boiling point temperature is less. And to cook the food, the time requirement is very high. So after that we are going to look at how this vapor dome came. Okay, the vapor dome, what is vapor dome actually? Vapor dome is a curve. Okay, curve of the simple, we join these 2 points, we join sensible. Generally how this vapor dome come, this curve came, PSTS curve. Okay, dome shaped curve came. Okay, so generally when we look that saturation temperature, what is saturation temperature? Saturation temperature is a temperature at which we decrease the, is a temperature at which the phase transformation will take place. Suppose for example 100 degrees centigrade at 1 atmospheric pressure, 100 degrees centigrade is the saturation temperature. So what is saturation? Saturated liquid. Liquid, for a liquid there will be pressure and temperature, right? Suppose for a liquid pressure is 1 atmospheric and temperature is 100 degrees centigrade. This is known as saturation liquid. Why? Because it exists in such a condition, that such a pressure and temperature, that at constant temperature if we decrease the pressure, then there will be a phase transformation of this particular liquid. Okay, I repeat that a liquid which exists at pressure and temperature in such a way that if the temperature is maintained constant, then if I decrease the pressure, then there will be a phase transformation takes place. Suppose for example, if a liquid is at 50 degrees centigrade at 1 atmospheric pressure, so once I decrease the pressure, does the phase transformation will takes place? Just look at the diagram. Does the phase transformation takes place? No, phase transformation will not takes place. Okay, if I decrease, then the temperature will also decrease. If I decrease the pressure, then temperature will also decrease at 100 degrees centigrade. If I decrease the pressure, what about the temperature? Temperature will be constant. If I decrease the pressure, then the phase transformation will take place. Okay, slowly the liquid is going to convert into vapor. Okay, so that is known as saturated liquid. All right, and same as saturated, same for the saturated vapor and saturation temperature. These three terms you know. Again, when we join, there will be a saturated temperature point, right? Saturated temperature points. If we join this all saturated liquid points, then you will get the saturated liquid line. Similarly, when we join all the saturated vapor points, you will get saturated vapor line. Once we join, these two lines will meet at one point, that is known as critical point. Okay, that is known as critical point. There is a main significance of the critical point. At the critical point, you notice that when you notice that pressure is increasing, the boiling point temperature is also increasing, and also latent heat for vaporization is decreasing. What is meant by latent heat? Latent heat is required for the phase change, right? The energy which is required for the change of the phase is known as latent heat. So you notice that latent heat is going to decrease actually. So at one point the solid will be liquid will directly convert into vapor. Okay, that is known as critical point. At pressure which is 221 bar and 374 degrees centigrade, the liquid is going to convert into lava, vapor. So in the boilers you may have noticed that boilers are maintained at high pressures. Boilers are maintained at high pressures. Why? Because this is the reason. Because in the boilers, why we are using the boilers? to convert liquid into steam. That steam we are expanding to get the work output, right? So the boilers are maintained at high pressure. Why? Because we need to convert the liquid into steam within a short duration of time, right? So we need to supply less amount of energy to convert into steam. So that's why boilers is maintained at high pressures. At high pressures, latent heat of vaporization is very less. By supplying small amount of energy, we can convert it directly into steam. Okay, directly liquid into steam. So there are three types of boilers you may have heard: supercritical boilers, critical boilers, and subcritical boilers. Supercritical boilers pressure will be greater than 221 bar. Okay, critical boiler pressure will be equal to 220. Subcritical boilers pressure will be less than 221. So generally in our NTPC it is pressure is less than 221. Okay, and in developed countries pressure will be greater than 221. There are certain disadvantages when we use there will be certain conditions under which boilers are designed. Okay, so in the developed countries they are using supercritical boilers, but in old NTPC plant it was pressure was 140 to 150 pressure boilers were used. Okay, this was a concept about how the TS diagram vapor dome came, and last thing you observe that what is the slope of this line, sensible liquid line. So sensible liquid line slope is positive and the slope is going to decrease, right? At one point slope is going to become zero. That's point slope. When the slope becomes zero, that is the critical point. Okay, and also you notice that in the saturated liquid vapor line, slope is negative and slope is going to increase and it is becoming zero. That is known as critical point. Okay, so this is all about the TS diagram. Okay, alright, so generally when we look at TH diagram, it is similar to the TS diagram which we had drawn. So next we shall look at PV diagram. Okay, generally when we look at this PV diagram, you may notice that there are constant temperature lines, right? But uh, generally we drawn one PV diagram for constant temperature. It was slope was actually when you look at the slope, when you look at the slope was actually decrease. Slope was negative, right? But generally when you look at this diagram is for phase change. All right, this diagram is for liquid. This diagram is for phase changing substance. This diagram PV diagram is for pure substance. Okay. So how to draw the PV diagram for PV diagram for the pure substance? Generally take one piston cylinder assembly. Okay, piston cylinder assembly vertical. Okay, you place the weights. Okay, you place the weights. Okay, isothermal process is very slow process, right? You generally place the weights uh, and slowly remove the weights. When you remove the weights, generally liquid is compressed, right? Now I am going to expand the liquid. So during the expansion of the liquid, once I remove the weights, then pressure is going to decrease. Okay, pressure is going to decrease. So pressure is going to decrease. So once the pressure is going to decrease, then what happens to the temperature? Temperature also decreases. To keep the temperature constant, we are supplying little amount of heat. When we supply the little amount of heat, there is considerable slightly increase of the volume may be seen. Okay, just you look at the liquid part. Okay, slightly increase in the volume will takes place. Now generally this process will carry out till saturation point. Saturation point, I told you, it is a point where if we decrease the pressure, then the phase transformation will takes place. So now if I supply the energy heat, then the phase transformation will takes place. Okay, phase transformation will takes place at constant pressure. Then after the liquid reach to vapor, then what happens? uh, what happens, sir? Generally again you can see the decrease in the pressure. Alright, decrease in the pressure and large increase in the volume. Okay, so this is how PV diagram we can draw the PV diagram. But one note point you write that this diagram is for ideal gas. No, sorry, this diagram is for pure substance, not ideal gas. Okay, for ideal gas we are drawn the isothermal line, right? Here it is different. So if we look at the temperature volume diagram, okay. So generally, initial state we are taking ice, which is at minus 20 degrees centigrade, okay. If we take the ice at minus 20 degrees centigrade, generally we are supplying the energy to the height to the ice, okay. Now ice is converting into 0 degree ice, so volume is increasing or decreasing? That is my question. So volume will increase or decrease? Volume is going to increase slightly because solids will expand on heating, right? So volume is going to increase slightly, okay. Slight variation will be there, right? So slight variation will be there, that is the thing. So generally, for example, if you take one water bottle, okay, I will explain this example, but uh, 0 degree ice, if you want to convert it into liquid, now I am going to supply some energy. Now what will be, what happens to the temperature? Temperature will be constant because ice is a saturated solid, right? Saturated point. So now what happens to ice? Ice going to melt. Ice going to melt, change, convert into liquid. Now temperature is what happens to volume? Volume of the ice will, volume of the water will decrease actually. Solids intermolecular solid in the solids intermolecular for distance is very less, right? When we heat, it converted to water. For the water, intermolecular distance is more. So it must solids on cooling, solids when converted into liquid, volume will increase. But in the water, in the case of water, it is not happening like that, okay. Generally, uh, generally what we are doing, to convert it into ice, generally we are taking water. Water is converted into ice, volume is decreasing actually. Why the volume is decreasing? Because uh, sorry, why the volume increases? First of all, if we convert from water to ice, volume, why? Because voids are created. So generally, if you convert ice into water, voids are get disappeared and volume will decrease, okay. For example, if you take water bottle, take one water bottle and fill the water bottle completely, okay. If you fill the water bottle completely, if we take place in the refrigerator, then what happens? Water is converting into ice. If water is converting into ice, then what happens? Volume will increase. Plastic bottle, due to elasticity of the plastic bottle will withstand that expansion, right? That stress. And generally, if you put in the steel cup, steel bottle, then that bottle will break, okay, because of the stress is expansion. Now you take the that bottle and keep it in the water. If you keep in the water, solids will expand on heating, right? So generally there will be heat transfer will take place. So general slightly remove the cap. What you observe? You observe that there will be burst, there will be pressure. You with more force the water will uh, come out. Okay, why? Because solids expands on heating. So generally you cool that water bottle, then cool that water bottle to the till it completely convert into water. Then you can observe that volume is decreasing. So the conclusion is don't ever put that completely fill the water bottle and put it in the fridge. Okay, that is the concept, okay. So generally, when if you look on the other angle, volume of volume of the water is less than volume of the ice, okay. When ice converted into ice, when water converted into ice, the ice expands, volume increases. So when ice converted into liquid, then the volume decreases because of the voids. So if we talk about the density of the water is less than the density of the ice. Sorry, density of water is greater than density. So that's why water bottle will float. If you take 1 kg of water, ice in 1 kg of liquid, then the water bottle will float on 1 kg of liquid. Okay, that is the concept. So again, next question is from 0 degree water to 4 degree water. If we add heat, then volume increases or decreases? Volume will is going to decrease. Okay, again it is going to decrease slightly. After 4 degrees centigrade, it is going to increase. Okay, so when you look at the questions, okay, so generally in the piston cylinder assembly, there is a weight is placed in on the piston, right? So there is an ice. So once you supply the heat to the ice, then the ice melts. When the ice melts, volume of the water will decrease. Once the volume of the water will work down on the system, piston will do work on the system on the water, right? So therefore work done will be negative and Q will be positive. So another interview question, one of the famous interview question was, generally when you take one water water jar. So when you put one ice, so when you melt that ice, then the water level will increase or decrease. That is the question. So generally, according to Archimedes principle, the water level will be same, because the volume displaced by the ice, volume is actually displaced by the ice, is the weight of the ice, right? Is the weight of the actually, when we melt that ice, the water volume will decrease, of course, but that volume of the water will come into the displaced volume. The volume of the water will be equal to displaced volume. So therefore, water level will remains same, because the weight of the water already displaced some volume. Okay, that is the point. Okay, so next to pressure temperature diagram. Once you look at the PT diagram, this diagram denotes for the normal substance. Okay, so generally when you are increasing the pressure, volume and temperature will increase, but at one point there will be phase change. So generally एक खासियत क्या रहती है डायग्राम्स की, कि द प्रोसेस लैटेंट हीट, इसमें लैटेंट हीट अपन बता नहीं सकते. यू कैन नॉट शो द लैटेंट हीट हियर. ओके, देयर वी कैन शो द लैटेंट हीट इन द पीटी कर्व. ओके, पीटी कर्व कौन सा था वो, PV curve. Okay, PV curve. So in the PV curve, once you notice that if we increase the heat, if we supply the heat, then the pressure is going to decrease. So during the phase change, pressure is constant, temperature is constant. So in the PT curve, how can we show the pressure and temperature constant pressure? So you can show it by the simple dot, simple point. Okay, so generally when I increase the pressure, boiling point temperature increases. At one point there is a phase change, and that during that phase change we can represent it with the point. Okay, so generally there are different processes. These diagrams are divided into two types: normal substance and for water. For normal substance, when we can see 1 to 2 process, 1 to 2 processes, liquid is converted into vapor. When liquid is converted into vapor, that is known as vaporization. When the vapor is converted into liquid, that is known as condensation. When the liquid is converted into vapor, that is known as vaporization. When the vapor is converted into liquid, then it's known as condensation. All right. So that curve is known as vaporization curve. So and when you notice A to B, then the solid is converting into liquid. When the solid is converting into liquid, that is known as melting. And when liquid is converted into solid, that is known as freezing. Okay, so again, when the solid is converted directly into vapor, that is known as sublimation. When the vapor is directly converting into solid, that is known as sublimation. Okay, those three curves. Okay, these curves denotes different things. Okay, once you need to observe that when liquid is converted into vapor, that is known as vaporization. When the vapor is converted into liquid, that is known as condensation. Okay, this is the diagram of PT curve for the normal substance. Alright, so generally now we are going to discuss about the various regions of TS diagrams. Okay, so first of all, subcooled region is liquid region. We can also call it as liquid region. Okay, so point in the liquid region is known as that point is in subcooled region. Okay, now how to know that if a point is on subcooled region or not? So first of all, you'll just look at T saturated. Okay, T saturated, he will give a P atmospheric or T saturated, T temperature. So suppose for example 1 atmospheric temperature, what is the boiling point temperature? 100. So if the actual temperature is less than the boiling point at saturated temperature, then we can say that point is on subcooled region. Similarly, superheated region, if temperature is greater than the saturated temperature, then we can say that point is on superheated region. Okay, so again, next is wet region in the sense the liquid plus vapor region. Okay, so the point is on T saturated will be equal to T actual, that is the point on subcooled region, wet region. Okay, so now let me ask you one question, that generally how can you define how many properties are required to define the system? Okay, how many number of independent properties are required to define the system in subcooled region? So two number of independent properties, whether pressure or temperature must be given, and also the actual temperature must be given. Okay, so that's how we can fix it, by using these two properties. Okay, whether pressure or temperature and T actual. Okay, next same pressure or temperature or T actual. So T actual is greater than T saturated, then we can say that it is in superheated region. Similarly, in the wet region, how many properties are required? Suppose one property is required. So if I give you the pressure, can you fix the system? If I give you the pressure, suppose P atmospheric pressure, can you fix it? So you can't fix it, right? You can't fix it.
Suppose if I give you pressure equal to 1 atmospheric, temperature equal to 100 degrees centigrade, can you fix it? You can't fix it, okay? So you require two properties, two independent properties are required, two dependent properties, not two independent properties are required, okay? So pressure or temperature is one property, and other properties required to you need. So we are going to define the another property, and again the question arises that entropy and entropy is a property, entropy is also there, no? So entropy will be the another property, entropy will not be the property, because entropy is a property, but we cannot find the absolute entropy, okay? So that's why we need to define the new property to define the wet region, okay? uh, so that property is known as drain extraction.
Alright, so next we are going to discuss about the drainage fraction. Okay, so ratio of drainage fraction, it is defined as dry. Okay, so how much ratio of the vapor is there? Mass of the vapor by mass of the total liquid plus vapor. Mass of the mixture is known as mass of the vapor to the total mass of the mixture is known as drainage fraction. X equal to mv by ml plus mv. Okay, this is known as drainage fraction. Okay, so generally there will be a vapor dome, right? So in between the two regions, saturated liquid line vapor, and there will be liquid plus vapor. Okay, there is a mixture of liquid plus vapor. So now generally, if we take the saturated line, okay, actually phase is not defined accurately. Okay, phase is not defined accurately, but we are assuming it is a saturated liquid. It is any liquid. Okay, only liquid. That means if a vapor is zero, if vapor is 0, 0 by 1, 1 plus 0, 0 by 1, dryness fraction will be 0. Okay, and if we talk about saturated vapor line, uh, mass of the vapor is 100%, that is 1. Okay, so 1 by 0 plus 1, it is 1. Okay, so you can notice that dryness fraction is started increasing. Okay, similarly dryness fraction value at critical point will be not defined. Okay, x is not defined at critical point. Similarly liquid fraction, okay, wetness fraction, liquid fraction is defined as mass of the liquid by mass of the mixture. Okay, so generally when we see saturated liquid line, then mass of the liquid by mass of the vapor plus liquid, right? Dryness fraction is 1. So dryness fraction slowly decrease and it will tend to 0 at critical point. Dryness fraction is not defined. Okay, so this is the concept of dryness fraction. So generally we were using the equation, right? We specific to find the specific volume vf of plus x into vg minus vf, s equal to sf plus x into sg minus sf. This we were using. Okay, so generally how we come to know about these equations. Okay, by using this concept, generally vapor is given by volume is given, volume of the wet stream is given by volume of the liquid plus volume of the vapor. So again specific volume, for to write in terms of specific volume we are multiplying with mass, right? So generally mass total mass into specific volume equal to mass of the liquid into specific volume of the liquid plus mass of the vapor to specific volume of the vapor, again divided with mass. So specific volume equal to ml by m. ml by m is wetness fraction, right? 1 minus x, 1 minus x into vl plus x into vl. Alright, so now here from here what we are doing, we are vl we are writing in terms of vf. Okay, for liquid we are taking the notation that is f, vl equal to vf, right? So vf plus x into vg minus vf. Okay, x into, for vapor we are taking vg. Okay, vl plus vf plus x into vg minus vf. Okay, Similarly, h equal to hf plus x into hg minus hf, s equal to sf plus sg minus sf. Yes, okay. So these are the equations. U equal to uf plus x into ug minus uf. Alright. So now we are going to look about the various points on the TH diagram. Okay. So generally a point on the superheated region. Generally don't get confused. Okay. So actually he took a point on the superheated region. Okay. So he took point on the constant pressure line. Okay. He is considering pressure is constant. Okay. So he point may be anywhere on the superheated region. He in the question number 11, grade previous year 18 2018 question. He didn't say that it is at constant pressure line. Okay, it will be at any point. So when the point is on his superheated region, we can generally how we can denote. When the point is on superheated region, for superheated region, T actually is greater than T actually is greater than T saturated. Okay. So how can you write in terms of enthalpy? Enthalpy suppose enthalpy at point 1 equal to h1 say. Okay. So h1 equal to latent heat plus delta H. Alright. Latent H1 equal to latent heat plus delta H. And latent heat can be written as Hg minus Hf plus delta H. Hg minus Hf plus delta H. Okay. Point is on saturated vapor line. The point is on saturated vapor line. Then H1 can be written H1 equal to Hg, right? H1 equal to Hg. H1 equal to Hg. Okay. H1 equal to Hg. Latent heat minus H1 gives you latent heat plus Hf gives you Hg. Latent heat plus Hf gives you Hg. Okay, Hg minus Hf gives you latent heat. Okay. So when the point is on wet region, generally when the point is on wet region, how we are going to define the point is on wet region. Okay. So when the point is on wet region, H1 will be equal to Hf plus x1 into Hg minus Hf. Alright. So H1 equal to Hf plus x1 into LH, because Hg minus Hf was LH when the point is on superheated region. Okay. I told you that H1 equal to Hg plus delta H. Now generally we are we are considering ideal behavior of gases. Okay. Since it is not a superheated stream, but yeah, we are assuming that it is an ideal gas. Okay. And also for point on the subcooled region, also we are assuming that is an ideal gas. Delta H, H1 equal to Hg plus CPV T sub minus T sat. Right, TC CP T sub minus T sat delta H CPDT. Right. So point on the subcooled region. Point on the subcooled region. Also we can write it as H1 equal to Hg plus Cp into T actual minus T sat. Okay. Now properties for subcooled region is not given. Okay, because it is not required for most of the cases. If nothing is mentioned, they will provide reference point. Okay, they will provide points P1, T1, H1. They will provide the reference points. Okay, now generally point is on subcooled region. Okay, he tells you to find at particular pressure is constant, right? At particular pressure, temperature will decrease. Right? Temperature will decrease. So temperature 45-degree temperature. It tells you to find out the right? It tells you to find out uh, enthalpy. So how to find out the enthalpy? First of all, you will give the reference point. You will just take one point. At one what point he is trying to ask. Just take one point and draw one horizontal line. Okay, touching the reference point one. Okay. So from reference point one, how can you find h1? H1 equal to u1 plus p1 v1. H1 equal to un plus p1 v1. Now it comes to find u1. What is u1? u1 is actually u1 at reference point. u1 is actually u1 at reference point. Why? Because it is a function of temperature for liquid as well as incompressible fluid. Okay, so u1 equal to uf. So find uf. To find uf, uf equal to hf. First of all, hf plus x into hf minus pf. Okay, hf minus pf. Find it. You will find uf just substitute minus pf plus pf gives you h1. Okay, v v1 v1 is equal to vf. Why? Because liquid is incompressible at subcooled region. Okay, right. Alright, so next, entropy. Similarly, you can calculate the entropy value. Okay, so for the entropy, first of all, mark the point. Okay, mark the point and see whether it is a phase change or it is in a saturated liquid line. Okay, or superheated vapor line, saturated vapor point. So then you just apply the equations for entropy. Okay, so now we are going to discuss one important topic. Okay, about the Mollier chart and reference point for the steam table. So in the steam table, properties are directly given. Okay, but generally in the stream tables you can find the absolute values hf, hfg, s2, sg. It means that they have taken one reference point. Okay, so yeah, generally in the ideal gases we took one reference point as absolute zero, but here they taken one reference point, that is the triple point of water. Okay, what is the pressure at triple point of water? It is 0.01 degree centigrade. 0.6117 Kelvin kPa. Temperature is 0.01 degree centigrade. At triple point, generally internal energy is zero, entropy is zero, everything arbitrarily they are zero. Okay, what is the enthalpy at what is the enthalpy at triple point? So to find the enthalpy at triple point, UF plus PF, it is nearly equal to 0.001. Okay, so now generally in the page number 319, 320, you can see that properties are given, right? Properties are given for liquid plus vapor. Okay, so generally when you know dryness fraction values and you know temperature values, you can find each and every property. Alright, so for each and every temperature they have given some value, set of values. You can find the dryness fraction and all. Okay, so in page number 321 and 322, if you know pressure and density, dryness fraction, you can find the same table. This is for liquid plus vapor region. Okay, phase change region. So 323, it is for superheated region, pressure and temperature. Generally how to find the enthalpy? It's 0.6 MPa 400 degree Kelvin Celsius. Enthalpy is 3270.8. That is the latent heat change in enthalpy HFG. So 10 MPa 311 degrees centigrade you can't find because you should know the dryness fraction at this point. Alright, because the point can be anywhere because there is a phase change, right? So practically uh, okay, so now we are going to start the Mollier chart. Okay, so in the Mollier chart diagram, generally different diagrams are not used practically, but practically we are going to use the Mollier chart. Alright, so and liquids are incompressible, right? So we are not concerned about the liquid subcooled region. Okay, we are not concerned about subcooled. We are going to apply the equations of incompressible fluids and to get approximate values. Alright, so X denotes the quality of the stream, right? So generally in the industrial molar chart, why we are using industrial molar chart when there is a complete molar chart? So in the industrial molar and industries, drainage fraction is concerned, is the main concern. Okay, quality of the steam is mainly concerned. So we in turbines, compressors, etc. we must use a good quality of steam, right? So good quality of the steam in the sense the drainage fraction must be greater than 0.9 and less than it must not be less than 0.09. Okay, so why it must not be less than, suppose if it is 0.7, then there will be liquid droplets. Due to liquid droplet there will be wear and tear in the of the components will take place. Okay, so generally people said that generally below 0.6 no industry will use, like major industries will not use. So if you want to use below 0.9, then you can go with the complete moisture, but generally from maximum it starts from 0.6 to 1. Okay, so that is the industrial molar chart. Now to discuss the different lines, you can see the constant pressure line, drainage fraction values, you know. Okay, that is a, so in the industrial molar chart you can see that liquid region is totally neglected, and half. And there is half liquid plus vapor lines. Okay, so first of all let's discuss about the constant pressure lines. Okay, you know TDS equal to dh minus VDP. Okay, if the pressure is constant, then dh by ds is equal to T. Okay, it is given by T. Okay, pressure of the constant pressure line is equal to T. Alright, so generally when you see in the phase change region there is a temperature will not change. Okay, right? So pressure lines are constant. Okay, pressure lines are constant. So after reaching saturated vapor, if we increase again, if we supply the heat, then temperature will increase. Okay, and pressure will also increase, enthalpy will also increase. So the points P1 P2 will diverge. Okay, and if you talk about T1 T2, same T1 T2, P1 P1 and T1 are same in latent heat, matlab phase change region. Okay, again the T1 T2 will diverge. Okay, so if you can see that temperature lines are horizontal. Why they are horizontal? Because at high temperatures the steam behaves like an ideal gas, so you can use the ideal gas there. Okay, so behavior of the ideal gas, so dh equal to cp dt. T is not changing, right? So the slope of the enthalpy will be constant. Okay, so that's why the lines are very horizontal. Also slope of the constant pressure lines increases. We are increasing the temperature, slope is increasing. Okay, this is all about the Molière chart and reference point of the steam table. Now we are going to solve some problems. Okay, so today I'm going to complete the first law and thermodynamics का किस्सा खत्म करना है. ठीक है, so generally I started with the level 2 questions. Okay, level 1 questions volume 2. So in the level 1 questions volume 2, if you look at the first question, okay, if you look at the first question perfectly, you just read that question. Okay, in this question I did a mistake. Okay, I don't did a mistake, but the temperature must be taken in Kelvin, right? Gamma times T2, temperature must be taken in Kelvin, and all the 4 problems I did perfect. Okay, so next one, that is level 1 questions. Alright, level 1 question, volume 2, level 2 question. Level 2 first question. Okay, when you look at the first question, there is a nitrogen gas. Okay, so once we open the wall, then nitrogen will do the work on the argon. Other side there is an argon gas. Okay, there is a piston. Generally the piston will be in equilibrium with the nitrogen gas. Okay, so generally to solve this problem, in the first part he asked about the argon gas. Okay, work done on the argon gas, work done during the process he asked, it will come negative, so it will come C or D. A and B are neglected. Okay, so generally I kept this problem as a review. Okay, I did this problem perfectly, first problem, but for the review I have put it. Okay, so work done by the argon gas can be given as argon gas will compressed, right? So work done can be given as dq equal to du plus dw. So dq will be 0, dw will be equal to du. All right, dw equal to minus du. M CV of argon gas and the temperature change of the argon gas. Argon gas temperature, initial and final temperatures are given. Okay, so that is dq. All right, that is dq. So next work done by the nitrogen gas. Okay, this is the I wrong question, right? Once you look at this question, generally I solved it perfectly, but work done work done by the nitrogen gas is given by work done for to raise the piston, as well as work done by the nitrogen gas, right? So to expand the nitrogen gas also, to raise the piston, to compress the organ, as well as to raise the piston. Okay, work done by the nitrogen. To raise the piston is raised to some height, right? 10 centimeter. So what is the work done by the nitrogen gas to raise the system will be added. Okay, mgh. So mgh is the energy, right? Potential energy. So m times g times h. Similar type of question I have seen, but I will relate it. Okay, within completion of this particular unit. So after solving all these questions. Okay, so mgh must be in meters, and he divided with 1000 times gc. Okay, 1000 times there is some I think there is a doubt. All right, so if you look at the third question I kept it in review, so I solved it. Okay, there are two ways to solve this problem actually. So generally dq equal to du plus dw, just apply that equation, or summation of q equal to summation of w according to first law. Energy neither be created nor but can be converted into one form to another form. For a cycle, summation of q equal to summation of w, right? This was the thing. So first of all, q, what are the losses? -1000 plus q dq equal to -1000 plus dq equal to this 0.5 kilowatt hour. First of all convert into seconds. 0.5 times 3 is example 0, that is 1800 -1800. Okay, work done is negative because it is, we are supplying power. Work done on the system, so -1800. If you take 1000 here, then it will be -800. -800 means it is temperature is increasing. All right, he transferred during the process he asked, so that is rejected actually. Okay, so heat transfer during the charging process is -800. Okay, -800, take care of the sign. So I kept in river, I did it perfectly. Next, in the second way, how to solve this problem? dq equal to du plus dw. So first of all, dq will be 0, du equal to dq equal to dw will be 0, and dq will be equal to du. So from here du will be equal to -1000, that is u2 minus u1 equal to -1000. Okay, so again, in the second process, dq equal to du plus dw, if I apply there, dw will be 0.5 times 800. Okay, du will be u1 minus u2, it will be minus of -1000, that is plus 1000, minus 800, 1800, that is 800. dq will be equal to 800. Okay, this way you can solve the problem. So again, next problem, see the problem number 5. Okay, look at the problem number 5. First of all, where is that problem? Okay, so he gave the efficiency, right? He gave the efficiency as 22%, and he gave the rated power output he gave 100. All right, rated power output he gave 100. Okay, determine the fuel consumption in liter. Rated power output in the sense reversible design. It is not desired, it is reversible, it is rated. Okay, so first of all, find the desired power output. Okay, so efficiency will be equal to rated power by desired power. Okay, first of all find out the power. Heat supplied will be equal to what is the power which is developed, okay? Pi. All right, so 100 by pi is q. All right, q, you will get q, right? I did this same, I did it in the same way, right? So mf into cv into qs, okay? So divide mf, will get a kg per second. Yes, mf, specific gravity times density of water. Specific gravity times density of water. Specific 0.8 to 820. That is pf, density. All right. So density, if you divide mass with density, you will get in meter cube. You will get volume. If you divide mass with density, you will get volume. How to find out the density? Density you can find out from specific gravity. What is the specific gravity? Specific gravity is the specific gravity is the density of fluid to the density of water. Density of water is 1000. Okay, and specific gravity has given as 0.82. 0.82 times 1000, it is 820 kg per meter cube. Okay, so if you divide it with the density, you will get volume, specific volume in meter cube. Okay, if you get in meter cube, that is in liter per liters. Okay, just convert it into liter per hour. Okay, this was the thing. Fifth question. Okay, so next sixth question. Sixth question was one of the good question. Okay, perfect question, I answered it, but no review. Seventh question, yes, seventh question is a perfect one. Eighth question, yes, eighth question also I did it. Ninth question, look at the ninth question. Okay, ninth question, you cannot solve by using that equation. Wait. Okay, if you look at the question number 9, okay, he told there is two compartments. Okay, after this compartment question, may you know, in finding TF, you should not face any difficulties. Okay, because you did maximum 3 mistakes in this thing. You can't make fourth mistake in that series. Okay, the first mistake which you did was actually by calculating CV. First, what you did, you calculated CV and you calculated N. You calculated CV and you calculated N. N equal to small m by capital M, right? So N he has given, small m you calculated, N times M. Again you did a manipulation, N times R bar by gamma minus 1 plus N2 times R bar by gamma minus 1 by R bar by gamma minus 1 plus R bar by gamma minus 1. You use this formula, but this formula was wrong actually. How it was wrong? Because he gave the CV value. Now what you did, you took that CV value and you directly put it and you find out n times n, number of moles times molar mass you calculated to calculate m, right? But that is also wrong, because you first of all look at the units of CV. CV is given as joule per mole Kelvin. Joule per, the only good thing you did in this thing is you converted joule into kilojoule by dividing with 1000. All right, so you didn't look at the unit of CV. CV is given as joule per mole Kelvin. That means that you can directly multiply n. No need to convert m into small n. But you directly directly substitute n CV dt, n CV t, n CV t by n CV1 plus n2 CV2. This was the formula, man. Calculation of final temperature you did in lots of mistakes. Okay, 4 mistakes I think you did. But the basic thing, the next how you should approach this type of problem. So first of all, look at the units, how to calculate, how to not to do the mistake in next time. You just look at the CV values. Okay, so whether he has provided the CV values, you judge it. Okay, yes, he has provided. You will do the mistake in calculate taking gamma and taking m. Okay, you just make sure that you don't make the mistake there. Okay, so calculate, don't, if you has given in number of moles, don't calculate in number of moles, don't calculate a CV value directly, just do n1 R bar by gamma minus 1. Okay, this was good thing. Okay, so I look at the units first of all, joule per kg Kelvin he has given, then you just calculate n. Okay, so that is the concept here. Okay, question number 9. Let's jump to question number 10. So in the next problem, Next problem, generally why I am analyzing these problems. Okay, generally how to solve the problems, one of the thing here, right? One of the most important thing, how to solve the problem. So generally there should not be any kitch, like you should not get stuck at the middle of the problem. Okay, you just like suppose for example you are calculating the density. You took the density as 1000. Again you realize that you took the density of water instead of air. Again you googled it and you search for the density and you took the density. So there there is a sudden gap, okay, sudden delay. All right. So while solving the problem there should not be any delay and any stucking. You took one value, right, that you realized and you manipulated that value and you took next value. Okay, this not work, this will not work. Okay, so the answer must be smooth, the solution must be smooth. Okay, put those problems, I mark those problems which you did smoothly. All right, the problems which you didn't do smoothly, if you get the answer but you review, you put for the review. Okay, you put for the review, that is the thing. So in this problem I did a mistake while calculating the density. First of all I took the density of water and next I took the density of the air. After I took the density of the air, then I took directly W as 0.1, but I don't look the key how much time it is taking. In how much time should I calculate the temperature. Okay, and rather I realized that later 8 p.m. to 1 p.m. it will be 5 hours. 5 times 3600 I multiplied with 0.1. So this is how I did this problem. But again I was getting first time I got the answer as 50 point something. Next I got a 51 point something, 58 point something, and okay, it was approaching 60.2. All right. So yeah, density of water you should, density of air you should calculate 1.101 point something. Pressure, atmospheric pressure. Okay, density equal to P atmospheric pressure, PV equal to MRT, right? MRT. V has given R. What do you need to calculate? You need to calculate the density. Mass you need to calculate, right? Mass. So mass will be equal to density times volume times RT. R he has given, T he has given, P he has given. Okay, volume he has given. Just calculate M. Okay. All right. So for this how you should calculate the value of density. You took 1.24224. So first then you took this 1.2. It was not good, but then you took 1 point, then after calculation we get 1 point something. All right. So I kept a review for problem number 6 level 1 question. Okay, so why I did perfectly, but कल के दिन भूल जा सकते हैं, कंफ्यूज हो सकते हैं. Okay, एग्जाम में कंफ्यूज नहीं होना. You know you should be sure enough, right? You should be confident to use the formula. Okay, so generally dq equal to du plus dw, this was a simple formula. अब ये इसमें डाउट क्या आया बोले तो जनरली कैन वी यूज द साइंस फर्स्ट ऑफ ऑल, और या डायरेक्टली इक्वेशन डाल के लास्ट में जो साइंस आ रहे वो साइंस यूज़ करना. दैट इज़ द थिंग. देख, generally first of all let's solve by without using the signs. Okay, dq he has given us 50 equal to du plus dw. Now dw we are getting negative वहाँ चले गया तो 40, du coming as positive 80, du is coming as positive 80, but that is wrong actually, right? That is wrong. ठीक है, that is wrong. ओके, अब दूसरा तरीका क्या है? स्टूडेंट इट डज अ मिस्टेक दैट डी क्यू इक्वल टू डी यू प्लस डी डब्ल्यू. क्यू का साइन डाल लियो, क्यू इज -50, बट डी डब्ल्यू का साइन नहीं डाले, डी डब्ल्यू का साइन नहीं डाले. उसमें क्या आता, आंसर नेगेटिव आता, वहाँ लेके गया था पॉजिटिव. दैट इज कमिंग एज राइट, पॉजिटिव नेगेटिव प्लस, दैट इज कमिंग एज -20. इज इट सो? वेट लेट मी चेक. पॉजिटिव साइन डाल लिया, डब्ल्यू का. आंसर इज कमिंग एज नेगेटिव. ओके, नेगेटिव वहाँ लेके गया था पॉजिटिव. ठीक है, Actually, I think you did a mistake here in calculation. That's why you got the right answer. Okay, this is actually wrong. Alright, wrong. So what you should do then? You will get negative. You should take positive, and no, don't do that thing. Okay. So generally, dw while calculating dw, if dw has provided you directly, he provided dw, then you will provide on the system or by the system. You can judge from there. You can judge the negative or positive sign there from there. Okay, but generally, when they gave you the initial and final points and all, right, you are calculating by using the formula, that is du equal to pdv. So in that, generally you are the sign is there. Okay, if you find 300 times 0 minus 0.2, your answer will become as minus. That means work done on the system. Okay, that formula itself decides the unit, decides the sign. Okay, you don't have to take the special sign there. Okay, you don't have to multiply with special sign, right? You just go with the formula itself contains the negative and positive signs, each and every formula. Okay, whether it may be constant pressure process, isothermal process, adiabatic process, the signs will be there in that formula itself. Okay, suppose for example 50 kilojoule work done on the system, you should take negative there. Okay, suppose 80 kilojoule work done on the system, you should take negative sign. Work done by the system 100 kilojoule, you have to take positive sign. Heat rejected by the system minus 50, that is minus 50, you should take. Okay, so dq formula if you are using, if he has provided, then signs will be included in that dq formula also. Okay, you don't have to take, but if he has provided the things, then it will be easy for you. Okay, so this was the question number 6, one of the good question. I think basic silly mistake you can avoid here. Okay, all right. So question number 8 I kept for review. Okay, uh, so review question, how to solve the review questions actually. So next, when you are coming for the revisions, D wrong questions, I wrong questions, D right questions, you will solve actually by using pen and paper. But what about review questions? Review questions are those questions which which you did right. Okay, which you did right, but there was a certain certain gap which is while predicting the concept. Okay, so actually for in a long run, you may again forget that particular point. What I have used here. Okay, in this question I solved it previously, but I use some concept here, so whether that concept is applied here or not, so that gap must be taken care of. So that's why I kept for review. While coming next time, you just read the question and you just find that point that gap. Okay, find that gap previously what you did. Okay, how you approach that question. Okay, that is a point. Okay, here in this question he has given us two equal volumes. Okay, I generally I looked for the temperature relations. There will be no temperature relations. Temperature T1 will be equal to T2. V1 by V2 equal to somewhat T1 by T2. I thought in that way, but that is not the thing. Okay, so he has given he should give the volumes actually, and he gave the values. Okay, he told indirectly, he told that it is divided into two equal parts. That is V1 will be V1, V2 will be equal to 2V2. Okay, that is 2V1. That is the thing. All right. Okay, so when you look at the question number 9, generally I did it right, but I kept for the review because I took, first of all I took V2 by V1 equal to T2 by T1. V2 by V1 gamma minus 1 equal to T2 by T1. Gamma minus 1 I judged correctly, but actually V1 it is inversely proportional, right? So V1 by V2 whole power gamma minus 1 equal to T2 by T1 it will be. Okay, that was a point where I missed. Okay, I look at the options and I thought that in the expansion process, adiabatic expansion process, temperature must not increase, temperature must decrease. Okay, so I was getting the positive value. Okay, so right, yeah, this was the thing. So in the adiabatic expansion process, temperature, if you draw temperature and entropy relation, then temperature will decrease means also pressure will also decrease. This is the TS diagram. Okay, properties of pure substance we will study, and we will look at this 9 problem, how to draw the PTS diagram. Okay, 10th problem, just find by using mdx plus ndy equal to 0. Okay. Okay, I calculated the result. Okay, it took nearly 5 minutes to solve this problem, question number 11. Okay, so when you look at question number 11, CP value has provided and temperature, gamma value is provided, M value, H and everything is provided. All right, so you just need to calculate CP value and T2 value. T2 value you can calculate easily, but I did a long procedure to calculate CP value. Okay, CP can be directly found out from gamma times R bar by M into gamma minus 1. You just use this simple equation, you will get it. Okay, I kept no, uh, it was D right question for me, D led right. All right. So while solving the question number 12, level 2 questions, okay, so in the while solving the question number 12, what I noticed here, the steam is accelerated by the nozzle steadily from low velocity to velocity of 210 at the rate of 3.2 kg per second. If the temperature and pressure of the steam of the nozzle, he has given each and everything he has provided, but he gave the superheat table actually. Okay, so generally when you look at this table, if the temperature and pressure of the steam at the velocity exit are 400 degree per centigrade and 2 MPa, okay, he has provided the exit exit area. Now he tells you to calculate the exit area actually. All right, so यहाँ पे कैसा लगा V2 low velocity, अच्छा velocity V2 he has provided, man. Reading the question, I did a mistake while reading the question. Okay, while reading the question, immediately wrong question, silly mistake. So 210 he has provided. Okay, 210 times 3.2 क्या हुआ किसको कौन कहीं को. Okay, so in question number 12, the problem was actually mistake was I didn't saw the data clearly. Okay, it was given velocity at exit velocity as provided. Okay, I calculated the velocity. Certain things I had right. Actually, देखो, I thought it was inlet velocity. If I thought it was inlet velocity, then the problem started. The error started. First assumption I made that he has provided the exit from the exit steam table, exit values. I took enthalpy to calculate C2. Then I thought that in the pressure will decrease, right? So I thought that initial inlet condition was different. So I took that thing. So from there I started doing the mistakes. So actually the data, we provided exit velocity. Once you provide exit velocity, then it becomes easy for you to calculate the exit area, right? Mass flow rate also it has provided. V2 you can calculate from exit stream table. Okay, right. So question number 13 I kept for review. Okay, so actually in this question, the basic mistake was P1 V1 minus P2 V2 by n minus 1. That is a mistake. Okay, first P1 V1 will come after P2 V2 by n minus 1. That is the formula. Alright, so today we are going to start with the determination of the tonnage fraction. Okay, so first of all we are talking about a throttling calorimeter. Okay, there will be a boiler drum in which there will be a wet steam. Okay, there will be a wet steam in the sense there will be liquid, also there will be a vapor. Okay, so yeah, so generally what we are doing at generally we are measuring its temperature and pressure with the help of the manometer before throttling, and after throttling we are going to measure its temperature and pressure. Why we are doing throttling I will tell you. Okay, so generally during throttling process is isenthalpic expansion process, right? So Throttling process is isothermal expansion process. We are throttling the wet stream to obtain the superheated steam. Okay, we are throttling the wet stream to obtain a superheated wet stream. In the superheated wet stream, you can you know that generally in the throttling the pressure will be reduced. When the pressure is reduced, what happens to the temperature? Boiling point temperature. Hmm. When the pressure is reduced, then the boiling point temperature will get reduced, right? Temperature will get reduced and the steam will be converted into superheated steam. So, and also by measuring the temperature and pressure of the superheated steam, enthalpy of the exit can be easily found out. Okay, so how we are going to find out the dryness fraction? We will look at we will generally see by using one problem. Okay, so if you look at the question number 8. Question number 8. So, a sample of the stream from the boiler drum at 3 MPa is put into the throttling calorimeter in which the pressure and temperature are found to be 0.1 MPa, 120 degrees centigrade. Find the quality of the sample taken from the boiler. Okay, this was the question. So, first of all, the pressure of the steam is 3 MPa. So, after throttling calorimeter in the sense after throttling, the pressure will decrease, right? So, after conditions are given, P2 and T2 values are given, okay? Find the quality of the stream as the sample is taken. So generally when we apply the first law, H1 plus Q equal to Q2 H2 plus W. If we cancel Q and W, H1 will be equal to H2. Throttling is an isenthalpic expansion process. So 0.1 to 120 degrees centigrade. At this point, find out the enthalpy. That will be H2 because this is the final condition of the steam. 0.1 MBA, and when you look at the steam tables. Uh, at 0.1 MPa 120 value degree centigrade, the values are not given. So generally at zero point 0.1 MPa 100 degree centigrade and 0.1 MPa 150 degree centigrade, the values are given, right? So using interpolation, you first of all find the enthalpy at exit. Okay, H2 will be you will get 2716.2. all right. So again, now what we are doing, we are generally we are finding H1. H1 will be equal to HF plus x1 into HFG equal to H2, right? So at 3 MPa, find out the values. All right, find out the values from the steam table. HF and HFG you find out. Okay, HG you find out. HF and HFG you find out. Wait. So again, notice that HFG. What is HFG actually? HFG is nothing but HG minus HF. Okay. So directly value he has provided HFG. Okay, 1794.9. Don't confuse here. You will be doing HG minus HF, right? So HFG value is directly given HG minus HF. Okay, so just calculate x1 will be equal to 0.95. So generally when you look at this x1, what does this denote? This denote that it is a good quality of stream, right? So generally what is a different method to find the throttling by using throttling calorimeter? So generally he will give input conditions like P1 T1, and he tells you to find out the dryness fraction. Now what you will do, you will just take the data and find out the H1. Once you get H1, then again HF less HFG, x1 Hg minus HF. You from here from second point 2, at point 2 you will find HF and HFG value, and similarly you will do the things. Okay, using the throttling calorimeter you can do the things. Generally what is the main of the throttling calorimeters? Using throttling calorimeter, what you are doing, we are generally converting the steam into superheated steam, right? So you are converting steam into superheated steam. So that's how you are going to calculate. The steam is converted into superheated steam. You will get the values by measuring pressure and temperature at the superheated condition. You will get by measuring pressure and condition. Actually, to measure the dryness, to identify the system, you need two properties, right? Either you should know pressure and temperature, and also dryness fraction you should know. But if you get to the superheated stream, with the help of the pressure and condition, temperature and enthalpies, you are going to find out the dryness fraction. Okay, so throttling calorimeter, what are the limitations of the throttling calorimeter? This method can be only used for good quality of steam. Why this method is only can be only used for the good quality of the steam? Why can't we use for bad quality, that is below 0.09? Because generally what is the concept of throttling calorimeter? We are converting steam, saturated steam, into superheated steam, right? Superheated steam. So when we
when we able to convert the steam into superheated steam, then using this superheated steam we are going to calculate pressures and temperatures, right? And we are calculating the enthalpies, and from enthalpies you are getting x1. Okay, three things you should know. To know enthalpy you should know dryness fraction. To find out enthalpy you should know pressure and temperature and dryness fraction. Okay, two properties you should know to find enthalpy, and the reverse is possible. To find out dryness fraction you should know enthalpy, pressure and temperature, right? So if you are doing throttling, then if you are not converting the steam into superheated steam, then how can you calculate pressure and temperature at superheated condition? Okay, you can't calculate, right? So that's why for the good quality of steam only it is possible. So question arises that, sir, how can we generally, how can we know that whether to use the throttling calorimeter or different to calorimeter? First of all, at exit conditions, just look at the temperature. Right, exit condition pressure, just look at the temperature. What is the temperature? If you are getting temperature as 120, then it is okay, right? It is, the point will be on above the vapor dome. If the point is temperature is 100 degrees centigrade, then it is saturated steam. Okay, it is not superheated steam, so you cannot use the throttling calorimeter. All right. Okay, so generally separating and throttling calorimeter. Generally this calorimeter is used when we do not have quality of steam, good quality, right? In this generally just look at the diagram. Okay, what is the concept here? Can I say that bad quality of steam is present, right? In the bad quality of steam, can I say that due to liquid the steam is converted into bad quality of steam? I mean that percentage of liquid is if increasing, then the quality of the steam will decrease, right? All right, so generally our basic idea is to remove the liquid from the steam. Okay, so from here we will start. Okay, from boiler, from main channel, we are extracting some mass of the steam, let's say m. Mass of the steam in the sense mass of liquid plus mass of vapor, right? So generally with the help of the gravity, I'm going to remove m1 amount of liquid, right? m1 amount of liquid. Due to gravity only liquid falls. Does the gas fall here? No. Okay, only liquid falls, m1. So m2 whatever the remaining gas is present. Okay, not all the gas falls below. Okay, so at 2 3. Okay, just look at the diagram and just to look at the result. We are calculating H3. What is H3? H3 is after throttling the steam is converted into superheated steam, right? So P3 T3, at P3 T3 it is H sub, that is H3. Okay, using the first law H2 equal to H3, you know this thing. Okay, and you can find the X2 value. Can I say that X2 is equal to mass of the vapor at second point divided by total mass of the steam M2? Can I say it? Right. So can I say M2 is equal to M2 of the vapor will be equal to M2 of the vapor 1, M2 of the vapor 2 equal to M2 of the vapor 1. I am removing only liquid, right? I am not removing the vapor. Okay, so just focus here. Okay, just focus here, just focus. Just focus. Okay, so generally let's solve some remove some misconceptions. So from first stage, when I am passing the steam, steam contains liquid and vapor, right? Liquid and vapor. With the help of the gravity I am going to remove the liquid. So when I say with the help of the gravity I am going to remove the liquid, you should not think that total liquid is removed, right? That is the one case. If the and also you should not think that at M2 there is only vapor. Okay, this is the second misconception. M1 in the sense M1 is only liquid. Okay, M1 it is only liquid, but that is not the total liquid of the which is present in the steam. In the steam there will be liquid plus vapor, right? High density liquid is removed, only less amount of amount of liquid I am removing, not the total liquid I am removing. Okay, steam contains liquid plus vapor. High density liquid I am going to extract, right? So at M2 there is a liquid plus vapor, there is a liquid and vapor. Can I say that vapor at 2 will be equal to vapor at 1? Because I didn't extracted the vapor. Vapor is as it is. Okay, vapor at 2 equal to vapor at 1. Yes. Okay, this is the only misconceptions. Okay, so now if I throttle from point 2 to point 3, at point 3 I'm going to calculate the H3. With the help of the H3 throttling process, with the help of the first law, I'm going to calculate X2. X2 is the dryness fraction at point 2, but we don't need the dryness fraction at point 2. We need the dryness fraction at point 1, right? So that's why how can we calculate? We calculate X2. What is X2 actually? X2 is the mass of the vapor at 2 divided by total mass M2, right? Mass M2, in the mass M2 liquid is also present and vapor is also present. M2 mv2 by m2. Okay, that is X2. Now with the help of this I am going to calculate X1. Okay, what is X1 actually? X1 is the mass of the vapor at 1, which is equal to mass of the vapor at 2. Mass of the vapor at 2 can be given as m2 times X2 divided by m1 plus m2. Okay, so this how we are going to calculate dryness fraction at point 1. All right, dryness fraction at point 1. These two methods can be used only when wait